Welcome to this lecture. In this lecture, we are going to continue discussing about convergence in probability. As we have been discussing about various modes of convergence of random variables, we have seen three types of convergences: convergence in LP, convergence almost surely, and convergence in probability. So, in the previous lecture, we introduced this notion of convergence in probability and looked at various reformulations of this convergence. We have also seen how this third type, this convergence in probability, is linked to the other two types. In this lecture, we continue discussing about convergence in probability, but our sole focus will be to obtain equivalent formulations, and we shall see later on that how these new reformulations help us obtain other further new results. So, without further delay, let us move on and discuss through the lecture notes. So, as pointed out, we are going to talk about equivalent formulations or equivalent conditions for convergence in probability. As these formulations are stated, we are always going to continue assuming that all these random variables that we are considering are defined on the same probability space, which we denote by some omega f p. Now, let us look at some of these conditions that comes up. Now, here what we are going to point out first is that if we just follow the definition, then convergence of a sequence x n to a random variable x in probability means that given any epsilon positive, the probability that modulus of x n minus x exceeds epsilon, that limit goes to 0 as n goes to infinity. Now, from this condition, it is entirely clear that we can rewrite everything in terms of x n minus x, this term. Now, earlier we have been focusing more on random variables x n going to x, but now we are saying that we are going to be interested rather in the difference, and our interest will be to show whether this difference is small or large, and that is what we are characterizing by the corresponding probability. And we want that this quantity should go to 0, and in terms of this convergence result that we have introduced, in terms of convergence in probability, x n minus x should go to 0. Now, here as always the 0 denotes the degenerate random variable supported at 0. Now, with this quick recollection of the definition, it is now the right time to state the main result of this lecture, and this is this, that we are going to continue with this probability space, and we have these random variables x and this sequence x 1 x 2 so on. Now, we are going to claim that there are several statements, 4 to be exact, which are these, that there are 4 such statements. The proposition states that all these statements are actually equivalent. So, let us just see one by one. So, the first one is our original definition of convergence in probability. Now, these other 3 are new, and these are in terms of either certain expectations or in terms of certain probability of certain events. So, let us see one by one. The second statement says that we need to look at this specific random variable, which is x n minus x divided by 1 plus mod x n minus x, and the claim is that in expectation these quantities go to 0. The third statement says that we have to look at these new random variables, which are the minimum of x n minus x with 1. So, by construction these random variables are already bounded above by 1. We are looking at the expectation of that, and the claim is that in limit these expectations go to 0. And the fourth type is slightly more complicated looking. This says that I have to look at all positive epsilon such that the probability of these event is less than epsilon, and we collect all such epsilon. So, that forms this set in this statement, and we are looking at the infimum of that. Note that when we are looking at this infimum, this quantity is depending only on n. and the statement says that as n goes to infinity, these quantities should go to 0. So, these are all these 4 statements, and the idea is that all these 4 statements are equivalent. So, let us see the proof of the first statement and the second statement, why they are equivalent. So, again we are starting with the proof of 1 implies 2 and 2 implies 1. So, without loss of generality, as we have already understood that we can always express everything in terms of x n minus x. So, therefore, what we are going to do is to assume that x is identically equal to 0. So, that is going to simplify our argument, but this is not losing any general cases, because everything is in terms of the difference. Alright. So, let us continue assuming that x is identically 0. Now, what we are therefore assuming is that we start by assuming that the sequence of random variables converge in probability to 0. Let us write down the definition, that we need that for every epsilon positive, this limit of these probabilities is 0. Now, with this observation, we now start doing certain manipulation. Our interest is to look at certain expectations of these random variables. So, we will first look at certain estimates of these random variables, and let us see what these random variables look like. First, what we are interested in are events of the type when x n's in modulus takes values greater than epsilon and less than equal to epsilon. So, these are the 2 specific events that we split our whole probability space, and therefore, we are simply writing 1 equals this summation. So, that is what we are doing. So, we are just rewriting the left hand side in terms of this right hand side. On the right hand side, we end up with 2 terms. On the first term, when modulus of x n is less or equals to epsilon, note that the term in front, that is dominated from above by modulus of x n. To see this, observe that modulus of x divided by 1 plus 1 by x, that quantity is always less equals to modulus of x. This follows since 1 plus mod x is greater or equals to 1. So, just use this and immediately we get this very simple inequality. So, that is what we use in the first term here. For the next term, we observe that again that ratio in front, which is again modulus of x n by 1 plus modulus of x n, that is dominated from above by 1. So, that is the domination we use for the second term, and we end up with just this indicator. So, therefore, the left hand side term which we are interested in has this upper bound given by the addition of these 2 terms. Now, note that the first term here has this very further next bound given by epsilon, because on this event modulus of x n is less or equals to epsilon, and therefore, we can now dominate the first term on the right hand side purely by epsilon, and the next term we keep intact. So, therefore, after all our arguments, we end up with these upper bound for the term of interest given by this quantity. Now, let us take expectation on the left hand side, and we end up with this quantity as an upper bound for the right hand side. Now, let us look at the terms. On the right hand side, we have that this quantity is going to 0 as epsilon is kept fixed and n goes to infinity, but then the idea is that we can always show that by taking n large enough, the quantity expected value of this ratio is therefore less equals to epsilon, simply because of the fact that this quantity goes to 0. So, therefore, this quantity is always less equals to epsilon, but since epsilon is arbitrary, we claim that therefore, this limit must be actually 0. So, that is what is the idea here. So, therefore, what we have done, we have started off with this ratio, we have obtained an upper bound, and then upper bound is in terms of epsilon, which can be made arbitrarily small, and therefore, this limit can be shown to be 0, which we wanted to show, and this proves that the convergence in probability, which is statement 1, implies statement 2, which is that this limit is 0. To prove the converse, let us start with assuming that the limit in 2 holds, meaning that this limit here, that expectations of these random variables go to 0 as n goes to infinity. Now, let us see what we want to show. We want to show convergence in probability holds, meaning we want to show this. Remember, we are continuing to assume that x, the limit, is identical equal to 0. This is again just the simplification we are using. Now, we want to show that this limit is 0 for all positive epsilon. Let us see again what we are going to do is to look at these kind of estimates involving the terms of interest. First, let us start with this term which we have information about. Now, here what we do first is that our interest is this specific event in question. So, let us look at this specific part of the domain. Now, for all those sample points small omega where modulus of x n exceeds this number epsilon, there we observe that this inequality holds, that the left hand side is greater or equals to the right hand side. But now, observe that we are using a specific type of a ratio and we have this function, that is what we are using here. Now, here what happens is that this function x mapping to x divided by 1 plus x, this is a monotone increasing function on 0 to infinity, and therefore, what we end up having is that these quantities, whenever modulus of x n is greater than epsilon, they are dominating these terms. So, therefore, this term on the left hand side has a lower bound given by this. Therefore, what we end up having is that this, using this monotone increasing function, these quantities are a lower bound for the left hand side, and let us take expectation here. Now, if we take expectation, then what happens is that these quantities on the left hand side is greater or equals to this right hand side, but now this is a purely deterministic term multiplying this specific probability that we are interested in. Now, we are given as per statement 2 that the left hand side quantities in limit go to 0, and therefore, as this quantity on the right hand side, this deterministic quantity is a positive quantity, we conclude that these probabilities must go to 0 as n goes to infinity. Therefore, we have proved that x n converges to 0 in probability as n goes to infinity. That is the proof for Roman 2 implying Roman 1. So, that completes the proof of the equivalence between 1 and 2. Now, this proof gives us some nice interpretations. So, that is what we are focusing on before moving on to proving the other parts. So, let us first look at this function defined on 0 to infinity. This is a non-negative function defined on 0 to infinity. Moreover, note that using this function we can restate the equivalence of 1 and 2 by this statement that x n converges to x in probability if and only if the function applied to this random variable modulus of x n minus x in limit goes to 0. So, this is the statement we are actually using here, and therefore, using this formulation what we are actually using are these specific properties of this function, that the function takes value 0 at the point 0, this is monotone increasing, it is bounded and it is continuous. So, we are using these properties of the function in our earlier proof. So, let us just go back to the proof once more to highlight these points once more. So, we have used the fact when we are proving from 1 to 2, we have used these monotone increasing properties and the bounds for this function here, and when going from Roman 2 to Roman 1, we have again used these properties for the similar calculations. So, therefore, we have used these properties that the function is bounded, continuous and it has monotone increasing property. Using these facts, what we finally conclude is that if we use any other function other than f, but with these same properties, then we can recover again the convergence in probability. In particular, what we do? We look at a new function again on 0 to infinity taking non-negative values. This function will be defined in this way that we take any such positive real number and send it to x minimum 1. So, this is the notation we will use sometime to denote the minimum of x and 1. So, the function g is defined to be this number that x maps to g x minimum 1. Now, here note that this function g is taking value 0 at 0, it is bounded, it is continuous, moreover it is monotone increasing. Therefore, we can repeat our earlier argument and obtain the fact that x n converges to x in probability if and only if this fact happens that g evaluated at modulus of x n minus x converges to 0 as n goes to infinity. Therefore, what we finally conclude is that using this function g we can characterize the convergence in probability. But note that by our choice of the function g which is x mapping to x minimum 1, we have actually recovered the third statement. So, we are actually by observing these relevant properties of the function, we actually have shown that the equivalence between the first statement and the third statement holds. So, essentially the proof that we used for the equivalence between the first and second statement, that is just using properties of certain underlying function which we written as f in that situation. Now, we are using a new function which we denote by g, and using the similar properties we now obtained the similar kind of a equivalence. So far we have shown the equivalence between 1, 2 and 3. Now, using these 3 facts we can get certain nice consequences of convergence in probability. Now, using these facts we are going to see certain applications which will actually lead us to an alternative proof of the fact that almost sure convergence implies convergence in probability. This we have proved earlier in proposition 2, but we are going to give you an alternative proof using the new results of the reformulations of convergence in probability that we have seen in this lecture. Let us start by assuming that x n converges to x almost surely. Then as a consequence what we will have is that modulus of x n minus x minimum with 1 converges to 0 almost surely. Now, here note that these random variables that we are using here, they are bounded. Therefore, as a consequence what we will say is that by the dominated convergence theorem their corresponding expectations will go to 0. So, that is the statement here, but this statement is exactly our Roman 3 which is equivalent to convergence in probability, which is this. So, therefore, if we start by assuming that x n converges to x almost surely by an application of the dominated convergence theorem and this equivalence that we have proved, we essentially have alternative proof that almost sure convergence implies convergence in probability. Now, we are left with the proof of the Roman 1 implies Roman 4. Now, here before we proceed with the proof, we make an observation that will make our proof technique simpler. Let us observe this fact that we have to handle this kind of terms in our proofs. Here we are using the probabilities of modulus of x n minus x exceeding epsilon. Now, here if this quantity is less than epsilon, those are the quantities we are listing in this set, and finally, we are looking at the infimum of this set. Now, if it so happens that this infimum quantity for some fixed value of n is less than gamma, then what happens? By the definition of an infimum of a set, we will find a number delta below gamma such that delta must be in this set. This is just by using the properties of an infimum of the set. Now, when we say that delta belongs to this specific set, we mean that delta satisfies this set building property, that probability modulus of x n minus x exceeding delta, that probability must be smaller than delta. So, this is just using the set building property that we already have, and since delta belongs to this set, this property must hold. Now, let us rewrite everything in terms of the parameter gamma that we have started off using. Now, note that the probability of the event that modulus of x n minus x exceeds this gamma, that can be dominated from above by the probability that modulus of x n minus x exceeds delta. This is true because delta is less equals to gamma. Therefore, whenever you have modulus of x n minus x exceeds gamma on that set, this must also exceed your delta. So, that is what we are using. So, therefore, the left hand side events that we are using here is contained in these events, and therefore, the probabilities are monotonically related in this way. Now, for the event involving delta, we already have an estimate upper bound through delta. Let us write that, but now further use gamma because delta is less equals to gamma. So, therefore, what we have ended up observing is that probability of modulus of x n minus x, this will be strictly less than gamma. What it says is that gamma must belong to this set that we have started off using. So, therefore, whenever you have that the infimum is dominated by some gamma, then for that gamma this property holds. So, this is the main observation of this note, and this is what we are going to use in our proof. So, again just to repeat, whenever this infimum of whatever this set is less than some gamma, then gamma is actually in the set, and therefore, the property is satisfied for the gamma. So, let us start with the proof, and that will finish off our lecture. So, let us see this proof. So, we start by assuming that convergence in probability holds, and we want to show that limit of these infimums will go to 0 as n goes to infinity. So, what do? We start by fixing a gamma positive. We are going to choose delta between 0 and gamma. Now, it is given that the probability of modulus of x n minus x exceeding gamma is 0. That is happening because x n converges to x in probability. So, we have just used the definition here. Now, corresponding to the delta that we have chosen here, there exists some natural number n just by using the definition of the limit that the probability is less than delta. So, here what we are using is that limit of certain real numbers is going to 0. So, therefore, for small enough delta, you must have a certain level, a threshold capital N, after which all the terms in the sequence are smaller than delta. This is just by repeating the definition of limit, that the limit is 0 and therefore, it must be close to 0, and that is what we are using here by looking at this error through the number delta. Now, for this delta we ended up having this bound. Now, therefore, what we ended up observing is that for all small n exceeding this threshold capital N, the probability of modulus of x n minus x exceeding gamma is less than delta, but that is for the less than gamma. This is simply because of the choice that delta is between 0 and gamma. So, that is what we are using here, and hence as a consequence we immediately have that gamma must be belonging to this set, because gamma satisfies this property. But this happens for all n exceeding this threshold. So, we have essentially rewritten the definition of convergence in probability, and we ended up having this property here. Therefore, what we conclude is that for all n exceeding the threshold capital N, the infimum must be less or equals to gamma, because gamma is in the set. So, the infimum must be less or equals to gamma. This is a very simple observation. Now, we started by assuming a arbitrary gamma, and that was chosen to be positive. And now, for that arbitrary gamma, we have obtained this threshold capital N such that this infimum quantity is less than gamma. Since this gamma can be chosen arbitrarily small, we claim that the limit of these infimum quantities must be going to 0 as n goes to infinity, and that is exactly the statement 4. So, by starting with convergence in probability, we ended up showing the fourth statement. Let us try to show opposite statements also holds. So, we now assume that the fourth statement holds, and we want to show that convergence in probability holds, and to do that we need to show that these probabilities for all gamma positive go to 0 as n goes to infinity. Now, we fix any such gamma positive and again choose a delta between 0 and gamma. Now, we are already given the statement 4 in this part of the argument. Now, given that gamma and delta, there exists a natural number n such that this infimum quantity must be less than delta for all n exceeding certain threshold capital N. This is true because the limit in statement 4 holds. Now, this infimum quantity less than delta means by our observation earlier, it will mean that delta must belong to this set, and in particular the probabilities of this event through delta, meaning modulus of x n minus x exceeding delta, that probability must be smaller than delta, and that is true for all small n exceeding capital N. All right, but let us rewrite everything in terms of the gamma threshold that we are interested in. So, now modulus of x n minus x exceeding gamma, the probability of that will be contained in the probability that modulus of x n minus x exceeds delta. This is because delta we have chosen to be in 0 to gamma, and therefore, for delta we can use the upper bound. So, that is what we write. Consequently, for all small n exceeding this threshold capital N, this quantity is less than delta, but this delta can be chosen to be arbitrarily small, and for this specific gamma and delta we have this threshold. Therefore, we conclude that the limit of these probabilities, that modulus of x n minus x exceeding gamma, that is 0, and that completes the proof that Roman 4 implies the first statement, the convergence in probability. So, therefore, we ended up showing the equivalence between all these statements, and here what we have is that convergence in probability can be reformulated in terms of these nice equivalent statements, two of them involving certain expectations of bounded random variables, and the fourth one was involving certain specific type of probabilities. All right. So, let us make one more important comment. So, we already have seen that one of these equivalent formulations gave us a alternative proof of certain earlier results, that almost sure convergence implies convergence in probability. Since we have these equivalent statements, these are giving better ideas about these convergences, and using these type of equivalent statements we are going to obtain other further interesting results. Now, we shall come back to these specific conditions again in later lectures, but one important comment is this, that these results that we have discussed in this lecture, they actually imply that convergence in probability is metrizable, meaning that there is a metric on the collection of random variables. In the metric, if the random variables converge, it is equivalent to convergence in probability. So, that is the formulation that we are going to discuss in a future lecture. We will come back to this issue later on, but in the upcoming lectures what we are going to see are further applications of these equivalent statements. We stop here. Thank you.